This problem is going to show you how to do problem 8 on the practice midterm. I took this from another textbook, and I think it's a pretty good problem in that it requires you to use many of the concepts from both Chapter 7 and Chapter 8, and you have to, it mixes them up, all right? So if you can do this problem, you have a pretty good grasp of those concepts. Let's read through it. So the Bank of Connecticut issues Visa and MasterCard credit cards. It is known that the balances of all Visa credit cards, so all is a very important word there because it's referring to everybody. It's a census, okay? So whenever you see that it's all credit cards, or all of the population, that means that you're going to be told parameter values. Okay, so all the credit cards have a mean balance of $845. And the standard deviation is 270. We're also told that the balances follow a normal distribution. That's not really plausible in real life. I would suspect that they're right skewed, but for the purposes of this problem, let's do what the book told us. All right, now I've scribbled this off to the left. So we're going to have X as a single credit card balance. So if I draw one person from the database, look at their balance, that is an X. Now we're told the mean of an X is $845. The standard deviation of these balances is 270, so sigma sub X. Now again, the reason these are mu's and sigmas is because it's coming from a census. Had this problem said something like we had a sample of several hundred credit cards, then this would be an X bar and an S. All right, but since it's from a census, these are parameters, they're mu and sigma. The distribution looks like this, it's normal, and I always like to label it down here. We have a name for this, we've been calling this the population distribution. Okay, let's read on. Part A reads, what is the probability that a randomly selected Visa card issued by this bank has a balance between 1,000 and 1,400. So the key here is to figure out what random variables is being asked about. So here it's a single randomly selected Visa card. So that's an X. So if we translate this into symbols, we want to find the probability that X is between 1,000 and 1,400. Now, I'm going to go draw this on the graph. So it's this region, the shaded region. Remember, probabilities always correspond to areas under a histogram. So we want to find the area of this. Now, whether you use a normal table or the functions in Excel or R, all of those things answer less than questions. So the probability that X is less than something. So we have to split this into two pieces. We're going to split it into the probability that X is less than 1,400. That's this arrow right here. Now the problem with that is we've included all of this area, which we don't want. So we need to subtract that off. So if we subtract the probability that X is less than 1,400 from the probability that X is less than 1,000, we'll get the slice that we care about. So let's go over to R and try that. So in R we use the p-norm function. So p-norm, and it's going to be 1,400. The mean is 845. The standard deviation is 270. That's going to give me this probability. Minus p-norm 1,000, 845, 270. And clearly I made a mistake. This should be 1,000. Okay. This is the answer. So 2630.2630. That would be the area in this region. If you're doing this in Excel, you just use norm dist. Exact same arguments, except you have to say true to whether you want a cumulative distribution. All right, let's move on. Part B now reads, what percentage of Visa cards have a balance of 750 or more. So we're talking about individual cards, so that's also an X. So we're asked, what is the probability that X is greater than 750? Well, let's go draw this again. It's the exact same normal curve. This is a distribution of X. It's the population distribution. We want to know what's the chance that we're to the right of 170. Well, again, R and Excel and normal tables only answer less than questions, so we have to use the complementary rule. This will be 1 minus the area that we're in this tail. So we can go find that in R. Let's go do that. 1 minus P norm. So it'd be 750, 845, 270. And so the answer is 0.6375. Good, let's move on. Part C. Okay, for the next couple of parts, assume that we've now drawn a sample of 100 consumers. So that's giving us our n, our little n. I've written that over here. Little n is that. And we've computed the mean balance x bar. So what is x bar? Well, x bar is just the sum of our 100 observations. So the first observations is an x. So I draw one value from this distribution. I call that x1. And I draw another value, so another person. That's x2. I do that 100 times. I add them up. I divide by 100. That's x bar. Question asks, what is the distribution of x bar? What is its shape? Mean, standard deviation. Okay, well, we need to remember some facts. I told you that the expected value of this x bar is just mu sub x. So when I draw these x bars, they're going to vary a bit, but on the average, I'm going to get the same mean as the mean of the population distribution, 845. Okay, now we also had some facts about the standard deviation of x bar. So again, this is called the standard deviation of x bar. Students have a lot of problems with the names of these things. So but it really makes sense. It's the standard deviation of x bar. So how dispersed is the distribution of x bar? Well, we had a theorem that said it was just the standard deviation of the population distribution, that's sigma sub x, or 270, divided by the square root of n. So as the sample size gets bigger, this distribution gets, more and more homogeneous, smaller standard deviation. So the standard deviation is 27. And then what is the shape? The shape is normal. The reason we know it's normal is because of what I call the normal theorem. If you sample from a population that's normal, the distributions of x bar and totals will also be exactly normal. The central limit theorem tells us something really similar in that the distribution of x bar sampled from any distribution is going to be approximately normal. Well, in this case, we don't have just any distribution, we have a normal distribution. So when we sample from normal populations, the sampling distribution, this is a sampling distribution, will also be exactly normal, not just approximately, exactly. So that's the answer to part C. Part D reads, what is the probability that x bar is now bigger than 875? All right, the key thing is to notice what random variable is being asked about. We're being asked about an x bar. We're not being asked about an x. So I'm going to, color this graph. Here's 875. We want to know what's the probability we're in this tail. I always like to write my standard deviation next to the graph because then I don't get confused about that. This is the distribution of x bar. The standard deviation of x bar is 27. Okay, so how do I find that area? Well, again, I got to use the complementary rule. We're going to flip this around. The area in this tail is just 1 minus the area in this region. Why is that? Well, the area under the normal curve is 1. So we can go find that in R. Let's go do that. So if I take 1 minus p-norm always gives me those less than probabilities, so 875. The mean is 845. Now get the right standard deviation, 27, not 270. 270 was for the population distribution. Here's our answer, 0.1332. So that's that area. Next part. Now next part's a little bit tricky. Given that x is bigger than 875, what's the probability that it's less than 885? Well, we have to remember some things about conditional probabilities. So it's saying, given that x bar is, given that x bar is greater than 875, what's the probability that it's also less than 885? So whenever you have a conditional probability, it's really the probability that both of these things happen, so this and this. So what does it mean to be greater than 875 and less than 885? It means that you're sandwiched between those values. Then we're going to divide that by the probability that the given happens. So what's the probability that x bar is greater than 875? Well, 0.1332. So let's try to visualize what this thing is asking for. We have some extra information. That extra information is that we are in this tail. We are somewhere in this tail. Now, if we're somewhere in this tail, what is the probability that we're in the slice relative to being in that tail? That's the way to think about this. So let's find the slice probability. So what's the probability that we're sandwiched between 875 and 885? Well, again, we split it up like we did back in part A. And so might as well go do this in R. This is going to be p-norm 875, 845. Now I've got to use the right standard deviation, which is 27. Oopsie, I made a mistake. This needs to be 885. Okay, less p-norm. Let's find the second one over here. 875, 845, 27. So the area in this little region right here is 0.064. So in other words, relative to the entire normal curve has area 1, the chance we're in this region is about 6.4%. Okay, but we haven't used the given. So now, what if we're told we're in just this tail? Okay, so how big is this slice relative to the entire tail? Well, it's 6.4% divided by 13%, so about 48%. So the conditional probability of being in this region, given that we're in this tail, is about 48%. The absolute probability, so not given any information, is 6.4%. Well, let's move on. Part F. Part F says the bank defines a small balance to be one that is less than $750. So the thing to notice is that we now have a dichotomous event. If I sample a balance, it's either small or it's not small. Suppose now we count the number of customers in a sample of 100 that have small balances. The important thing to do here is to recognize this as a coin flip. So I flip the coin 100 times. I look at 100 balances. Each balance is either a head or a tail. So either heads it's small, tails it's not small. So what is the distribution of this count? Well, anytime we flip a coin some fixed number of times and count the heads, it's a binomial. So find its mean and standard deviation. Well, let's see. We need to know the probability of a small balance. We've already kind of found that from part A. So we just take, part A was asking what's the probability, sorry, part B. Part B was what's the probability it's greater than 750. Well, 1 minus that gives us the probability of a small balance, so 36%. If you want, you could go back and type this in. So it would be 750, 845, 270, and we get the same number. All right, we did that earlier. So if XB is this binomial count indicating the number of small balances, then the mean of XB, we had a theorem saying it was just n times pi. Therefore, we expect 36 small balances out of 100. What's the standard deviation? Well, it was n times pi times 1 minus pi. Go plug those numbers in. Standard deviation is about 4.8. All right, part G now reads, what's the chance that 40 or more people will have small balances? So we're asked about the number of small balances out of 100. So it's really saying, what's the chance that our binomial count is greater than or equal to 40? Well, all of these functions answer less than questions, and whether it's Excel or R or tables, they only do less than. So we have to convert this to a less than. Since the binomial is a discrete distribution, we have to be really careful about our equal sign. So the chance that we have 40 or more small balances is just 1 minus the chance that we have 39 or fewer small balances. All right, so we can find this using p binom. So we can do it exactly. So 1 minus p binom. So I want 39 or fewer heads. I have 100 flips, and I'm just going to type in the number. So 0.3625, there might be a slight amount of rounding there. The answer is about 24.79%. Well, we could also use the normal approximation. So why don't we do that? This would be 1 minus. Now I care about the bar over 39. So that bar runs from 38.5 to 39.5. So I'll use 39.5 here. Subtract the mean I found back here in part F. Divide by the standard deviation. And if you then type those numbers into R, might as well go do that. This will be 1 minus p norm. So 39.5, the mean is 36.25, the standard deviation is 4.8075 or so. The answer is 24.95%. That's an approximate answer, which is why I sort of dotted it and wrote it in lighter ink. We're really close. So we're accurate to 2, almost 3 digits. So I think that's a good problem because it makes you keep an X. So parts A and B were about a single credit card, separate from the mean of a bunch of credit cards, an X bar. That's what those next parts were about. And then parts F and G talk about small versus large accounts.